been tossing between when I've introduced the theorems to you, do I also want to show the proofs or just do an example? And I decided I'm just going to give you the formula, and then we'll do an example. If you want the proof, then send me a message, and I'll create a whole video just of the proofs, because the proofs will take much longer time because of the intricacies that we have to follow. So what do you want to do? You want me to do the proofs, or just show you the mechanics, nuts and bolts, and how to do the shortcuts?
What's proofs?
Each step of how they got the general formula.
You know what? Let's do it.
Okay. All right. Go through all the different types of functions that we encounter. We're going to look at constant functions. We're going to look at linear functions, polynomial. So we have exponential. We're not going to do logarithm just yet. And we're not going to do trigonometric just yet. So we'll just stick with these. Oh, yes. Linear power and quotient. Remember, in the past, if I gave you a function that looked like this, what would you have to do to find the derivative? You have to do the limit. Remember, you have to first find f of x plus h, you have to plug it in there, work it all out, take h goes to 0, a lot of work. Now, all that stuff is gone. The first one, let's talk about the constant rule. If you're given a function of a constant term, the derivative of this constant term is 0. Can you guess why? And this is all algebraic. We're going to do this discussion here. Yes?
There's no x to multiply with?
It has to do with the graph. I see where you're getting to. That would help in the other ones, but not this one. Let's say, for example, if I gave you a function f of x equals 3, what's the derivative? Okay, now let's look at this thing. Let's look at the graph of this function. What does f of x at 3 mean? What does that look like? What kind of function does that look like? So horizontal line. Because remember, f of x is the same thing as y. So no matter what value x you give me, what does y equal? So no matter what x you give me, y is equal to 3. Therefore, it's a horizontal line. So that's f of x. F prime of x finds what? What does the derivative find? The slope. What's the slope of that line? Thank you, thank you. Linear function. F of x equals x. What does that graph look like? You like the vertical lines, don't you? No.
I mean like a diagonal line.
Keep into it. John Travolta, go on. Staying alive. Yes, it's a diagonal line through the origin. What's its slope? Because when x is 1, y is 1. When x is 2, y is 2. The slope is 1. A constant multiple of a linear function. What does that mean? Constant multiple. If I gave you that. Sure. Is this a linear equation, a quadratic, or what? And how do we know? Why is it linear? How do you know it's linear? Yes, exactly. Because the exponent on the variable is 1. And we know the linear equation is of the form y equals mx plus b. So what do we know about this graph? What's the y-intercept? It doesn't have one, so it's 0. It goes through the origin. What's in front of the x? The slope. And our slope is what? Up 3 over 1. So the derivative is 3. Yes, a constant function would have had derivative of 0. But since we have a constant multiple of a linear equation, it's the same as we do with the limit function. Remember, we take the limits. If you have a constant, it goes in front, and you take the limit. That's the same thing you do here. You take this value, put it out in front, and take a derivative of this. What's the derivative of x? 1. So 3 times 1 is 3. Pretty straightforward. See, it beats doing that limit as h goes to 0 by 1,000,000%. So if you have a linear equation, the slope is whatever the coefficient is. So far so easy? Let's look at the power rule. The power rule says this. Given any function of x raised to some power, the derivative whatever the exponent is, bring it down and subtract 1 from the exponent. Example. X to the power 6. What's the derivative? Pretty fast, isn't it?
Yep.
Remember the ones we did last time. We did functions like this. 1 over x and the square root of x. That took a lot of work because in this one we had to multiply by the conjugate, simplify, and then take h equals 0. This one, we had to do 1 over x plus h minus 1 over x and get the common denominator. A lot of work. What we have to do here is we can use the power rule to solve this one. How do we put this function, rewrite it with respect to an exponent, to a power? Very good. Because x is down there, since I bring it up to the top, it becomes x to the power negative 1. Now we can use the power rule. What does the power rule tell us to do? Bring down the exponent, and then subtract 1 from the exponent. We have negative 1, x to the power what? Negative 2. So what's the derivative? Negative 1 over x squared. Again, don't forget the negatives. That's the part that's really going to hurt. What will help, a lot of times when we do this, put parentheses around the numbers that have negatives. Because you know they have to stay together. Didn't I tell you this is going to take no time at all compared to those? But we had to go through that rite of passage. Now you appreciate that stuff. How about this one? Somebody who hasn't answered one yet, preferably in the back row. Anybody not wearing a red shirt? I'll go either gender. I'm not discriminatory. Excellent. Very good. A radical is x to the power 1/2. So the derivative would be what do you do with the exponent? Bring it down, so it goes 1/2. And what do you do with the exponent? Subtract 1. So this is the same as 2 over 2. So it's negative 1/2. Can you rewrite this? Remember, you don't want to have negative exponents. Or 1 over which becomes, and there's your derivative. See if I have any more examples here of different types of problems. Here's one example. How about if I gave you that? Find me the derivative. There's your constant multiple. Bring down the 4, and then 4 minus 1. 12x to the third. And there we have it. That's our derivative. That's the slope. You have to, because when you bring it down, remember, that's a constant multiple. It multiplies with whatever we have here. So when we bring down the 4, it has to multiply with 3. Because if not, it'd be 34, and that's totally wrong. You got it?
Yeah.
All right, I found my examples I wanted to show you, make y'all do. F of x equals x to the power 2/3. No. No calculators. Well, the calculators will only give you decimal answers. We don't have any decimal answers here. We always have either rationals or integers. First step, bring down the exponent. So it's make it your coefficient. And then for the exponent, you have to subtract by 1. So 1 is the same thing as 3 over 3, because we have a denominator of 3. 2 minus 3 is negative 1 over 3. What happens to this one?
2x.
If it's negative, it goes to the bottom, so you make it positive. What does a 1/3 exponent look like? What does it become? Cube root, very good. Cube root of x, and there's your derivative. Everybody okay so far? Nobody's ever died in this class because of this. Now we're going to change the way they look. If I'm going too fast, please tell me to slow down. X to the power radical 2. It's there. Exponents could be any value, any real number, which means it could be rational, irrational, it could be anything. There's really only 2 steps you have to do. What's the first step? Bring down your exponent, which is radical 2, and then subtract 1. There's your answer. Radical 2 minus 1, unless you have a calculator yet, but it's as good as it gets. One over x to the 4th. First step.
Change it to x negative.
Right, rewrite it as an exponential function. Then
Bring down the power to the coefficient.
Very good. And then what do you do up here?
Subtract 4, -4.
Minus 1. Subtract 1. So it becomes -4x to the power what? So to simplify this, we would rewrite it as
-4 over x.
And there's also a pattern that's looking here. Whenever we have rational functions to an exponent, it started as x to the 4th, ended x to the 5th. We had 1 over x, it ended up x squared on the bottom. So whenever you have a rational expression, your denominator increases by 1. Now, yes? It wouldn't be wrong, but the common convention of mathematics says you never want a negative exponent. But with that convention of mathematics also says you never want a radical on the bottom, but they leave the radicals on the bottom. So, bless you. I will take it either way, but I think the computer may say, no, I don't want it. But yeah, try both ways. I mean, if it works both ways, then great. One more. Radical x 2 plus pi inside the radical. This will test your algebra knowledge. What's the first thing you got to do? What did we do last time we had a radical? Yeah. You only bring it forward in the front if you're taking a log of them. What do you do when you power to a power? Yeah, when you have a power to a power, you multiply the exponents. So multiply both of these by 1/2, you get 1 plus pi over 2. Yeah, so your first step is clean it up, make it functional. You can only have one exponent. Now we could bring down the 1 plus pi over 2. It's pi over 2, subtract 1 from it. We can't do anything with the coefficient now, so leave it as 1 plus pi over 2. What happens to our exponent? Do we need the parentheses? No. So we have 1 plus pi over 2 minus 1. What happens to the 1s? They cancel. So what we're left with is over 2. Are we done? What's the last thing we can do? Very good. Because pi over 2 is the same thing as pi times 1/2. So if you have an exponent of 1/2, it's a radical. So it's the square root of x to the power pi. And there's your derivative. This, again, as I said, the hardest part of this course is going to be remembering all the algebra and the trig rules. The calculus part just starts it. The rest is algebra. Any questions so far? Let's move on to what's called the sum and difference rule. Let u represent the function f of x, and v represent the function g of x. They're two independent functions. The derivative of u plus v with respect to x we have both of our functions, is because it's the sum of the functions, then we can take the derivative of the sum individually and add them together. In one short sentence, it says the derivative of the sum of two functions is the sum of the derivatives of those functions. So the derivative of the sum of two functions is the sum of the two functions, the derivatives of the functions. Let's see what that means. F of x equals 4x cubed plus 5x squared. What's the derivative? So what the rule says, since we have two terms here, we take the derivative of each term separately. What's the derivative of this one? 12x squared. And derivative of this one?
10x.
There you go. How about this one? We're looking at the difference of two functions now. There. The derivative of the first one is
12x. Negative 12.
yeah.
No, negative 12x.
Negative 12x cubed, because you bring down and then subtract 1. Then, what sign?
Negative
Minus. And then the other derivative.
15x.
And it doesn't matter how big of an equation you have. Make that minus. Find me the derivative of this function. How many derivatives are we going to take here? One, two, three, four. We have 4 terms. So what's the first derivative?
3x.
Second derivative?
Uh,
8 over 3, yes. Just bring down the 2. 2 times 4 is 8. Next one? Last one.
0.
That's it. Very good. So far, so easy? Yeah, I mean, remember, keep these rules handy, because the more you do them, they'll become memorized, but they're going to save you so much time from here on out. Which means the functions are going to get more complex. Next rule. Exponential rule. This is an easy one. Yes, I know some of you are going to ask me, well, this is only one factor. Anybody remember what E is? What it's called? It's called Euler's number. Euler's number. It's used whenever you have an exponential, a polynomial of some order, you're trying to find the rate of change of one point along those curves. Sometimes they don't exist. So Euler came up an approximation of a value. Basically, what it is, if you took the original exponential function, a to the power x, the limit would be taken as h approaches 0. What does this graph look like? It's an increasing function. It always crosses, when x is 0, y value is 1. So the slope of the curve at the y-intercept, it equals 1 whenever the base is 2.718. That's where we got this. So with that, the derivative of Euler's number of the exponential function e to the power x is e to the power x. We get to a point later on, because right now we're keeping the exponent as just x. If we had e to the power 3x, the derivative would be 3e to the power 3x. We'd have to take a derivative of the exponent. But that is coming up when we do chain rules and combinations of those. Do we have any examples for that one? Yeah. Let's see what else we want to. Oh. Products and quotient. This is where things start getting, yeah, it takes more memorization now. So there's a special rule. I'm going to show you the one I use, which is good for both of these. Other than that, they may try to make you memorize some convoluted way, which always gets the signs mixed up. Let u represent the function f of x, and v represent the function g of x. If we had a function where the product of two separate functions, the derivative would be v u prime plus u v prime. What does this mean? Well, the first one, we have f of x and g of x. Say h of x is equal to f of x times g of x. The derivative would be g of x times the derivative of f of x plus f of x times the derivative of g of x. You see why I used u and v instead. The examples I have. Oh, there they are. Take an example here. F of x equals 1 over x times x squared plus e to the power x. This is a product of two functions. This is the first one, that's your u, and that's your v. Or f and g. Now, here's the way I suggest you memorize it. You have the two functions. U is 1 over x, and v is x squared plus e to the power x. Take the derivatives below there. Write the derivatives below those respectively. So what's the derivative of 1 over x? Negative 1 over x squared. When we talk about the quotient rule, we'll see why the bottom increases by 1. What's the derivative of v, the second function? What's the derivative of this one? What's the derivative of this? So that's the easy part. Now comes the easiest part, putting it all together. Everybody know that little, I call it the Jesus fish. You know what I'm talking about? That. So with that, it works here also. Start with this one. Go down, you go to u prime. Since you're multiplying, it's making it bigger, we add. So we go to v to u, and then u to v prime. Take them in that order. So v is x squared plus e to the power x times negative 1 over x squared plus 1 over x times 2x plus e to the power x. Any questions so far? Now we just have to clean it up. Distribute that one, so we get negative x squared over x squared minus e to the x over x squared two x over x ex over x. Simplify. What happens here? Negative 1 is ex over x squared. How about here? Those x's cancel. E to the x over x. Combine like terms. Negative 1 plus 2 is 1. Looking at these two, what do we have? If we make them common denominator, can we make them common denominator? Will that matter? Do we factor out an x out of this one, or do we multiply this one by x over x? Either one works for me. Okay, if we factor out an x, taken care of. We have two terms here. What can we factor out of those? What do they have in common? E to the x over x. That leaves what inside there? Actually, no. Since I took out the negative, I got to change this sign. I factor out a negative ex over x. I have to change this sign when I factor it out. So there's your simplified version. When you have an x, just plug it in there and you're done. Okay, let's look at another example. Y equals e to the power 2x. What's the derivative? Take a derivative of the exponent, gives us 2, and just leave e to the power 2x. There you have it. The quotient rule. h of x equals f of x over g of x. Remember, okay, whatever the functions are, you have f of x and then g of x. Take the derivatives of both of those. So now we're looking for the derivative. We do the same format we did last time. G of x times f prime of x. Now, since we're dividing, what sign goes between there? Subtraction. So it's g of x times f prime minus f of x times g prime. All over the denominator squared. So list your numerator, your denominator, and the derivatives of them. And then do the fish, you'll never go wrong. You just have to remember, if it's a product rule, you have to add them. If it's a quotient, you subtract them. Here's the example question. F of x equals t squared minus 1 over t cubed plus 1. When people get stuck, they still try to look busy. So the first thing we have to do is the numerator is t squared minus 1. The denominator is t cubed plus 1. The first derivative of t squared plus 1, or minus 1 is what? 2t. 2t. The derivative of the second one? So the derivative of this function derivative of t squared is what? Derivative of 1 is what? 0. Yeah. So any constant disappears when you take a derivative. Good question. I'm glad you asked that, because I know everybody else, a lot of people are thinking, where did it go? But yeah, that's what we talked about earlier. You can, if you have multiple terms inside an equation, you take a derivative of each term separately. The derivative now is take the g, which is t cubed plus 1, times f prime, which is 2t. What sign goes in the middle? Subtraction, since we're dividing. Go to f, which is t squared minus 1, times g prime, which is 3t squared. All over g, which is that, squared. So it's f prime is g f prime minus f g prime over g squared. This is the shortcut of it. Now let's do the algebra part. 2t times that, so it's 2t to the 4th plus 2t. 3t squared times t squared is minus sign, minus 3t to the fourth. Negative 3t squared times negative 1 is a positive 3t squared. And don't factor out the bottom. Leave it alone. Leave it as a square term. The reason you want to do that is because it's much easier to find your asymptotes this way than if you expanded it. So leave the denominator as an exponential function. Combine like terms on top. 2t to the 4 minus 3t to the 4 is negative t to the fourth plus 3t squared plus 2t over t cubed plus 1 squared. And that's your derivative. Easy? Imagine doing this to the limit function. X plus h divided, it'd be painful. Oh, let's look at another one. I know we've done this one before. E to the power never. Make this one into a quotient function. Take the derivative of it like this. So we have the numerator, which is 1, the denominator, which is e to the x. The derivative of the numerator is what? 0. The derivative of the denominator is ex. So the derivative of our function is g, which is e to the power x times 0 minus 1 times e to the power x over the denominator squared. Far so good? That becomes 0, so we have negative 1, or 1 times e to the power x is e to the power x. E to the power x over 2 on the bottom. Can anything cancel? Well, there's 2 e to the x's here, there's 1 up there, so I can get rid of one of those. What I'm left with is negative 1 over e to the power x. That's my derivative. Which would have been the same thing had we done it the other way. The derivative of this exponent is what? The derivative of negative x is negative 1 e to the power negative x. So it's negative 1 e to the power x. Now, the problem is this. You have a lot of steps, a lot of tools you can use. Oh, let me hold off on this, because I'm going to give you one question I want everybody to work on and bring it back on Monday. And I'll bring some candy. Whoever gets it right will get a piece. Whoever gets it wrong could watch me eat them. All right, so let's see what else. Are we stuck with only taking one derivative? No. Here are derivatives. Let's say our initial function starts off x to the fifth. We take a derivative of it. What do we get? Let's take a second derivative of that. What do we get?
20x third.
Let's take a third derivative of that.
60x squared.
Let's take a fourth derivative of that.
120x.
Let's do a fifth.
20?
Yep.
Yes.
What would the sixth derivative be?
0.
0. So just repeat the process. Once you find the function, you can find the first derivative. Repeat the same process so you can find the second derivative, third derivative, fourth derivative. For example, trigonometric functions are infinite. You'll never run out of derivatives. Because all they do is switch from sine to cosine, sine to cosine, positive sine, positive cosine. So, but with linear functions or exponentiated functions, they do run out of exponents. Everybody okay with the higher derivatives?
Yeah. Thank you.
Here's your second problem. On the top, x minus 1 times x squared minus 3x all over x to the fourth. Find me the first derivative. I was going to say find me the second derivative. Because in order to get the second derivative, you have to find the first derivative, right? But, no, I want you guys to get some sleep this weekend. This is where we end today. With a demonstration. That's what I wanted to show you.